Hi friends, welcome to DCBA. Today I'm going to show you a MDM shortcut. I hope you have seen the thumbnail of this video and you have come here, and that is what we're going to start with. That is MDM in one step possible? The answer is yes, it is possible, but with terms and conditions. Now what are these terms and conditions? There is only one term and condition, that is structure needs to be symmetric. Now comes the question that what is a symmetric structure. So in first few minutes of this video we are going to talk about what is a symmetric structure, how to recognize a symmetric structure, and then we are going to start with our actual MDM process. So let us see this example. This is a frame with two columns here of 5 meters, and the moment of inertia I for both the columns, and this beam of 4 meter length. Now is this a symmetric structure? So yes, it is a symmetric structure, and how to recognize that? We draw a section XX right at the center of this particular structure, and we'll have to check that the left side of the structure should be similar to the right side of the structure. The entire left side should be exactly similar to the right side. In this case it is similar, therefore it is a symmetric structure. Let's check another case here. Now is this a symmetric structure? Let's check it. We again draw a section at the center of this beam. The left side of the structure has a column with moment of inertia I. Here the moment of inertia is 2I. Though the length of the or the height of the columns is same, that is 5 meters, even the beam is 4 meters, that is 2 meter here, 2 meter here. So beam is also similar, but the moment of inertia is varying, that is I and 2I. Therefore this is not a symmetric structure. Let's see one more example. Here again let us draw a section. So both these columns are similar, that is having a 5 meter height as well as similar moment of inertia, but in the beam the moment of inertia for the first 2 meter span is I, and then it changes. So it's a varying cross section, and therefore it is not similar or not a symmetric structure. Is this a symmetric structure? No, it is not. Although it contains the properties of what we saw earlier, that is these two columns are of a similar height and of similar cross section. Even the beam is having a cross sectional, equal cross sectional throughout. There's 2 meter here, 2 meter here, but the loading is not similar on both the sides. So with the geometry of the structure, my loading should also be similar on both the sides. In this particular case we have loading only on left hand side, and the right hand side does not contain any loading. That is why this is not a symmetric structure. Is this a symmetric structure? Yes, it is, because with the geometry complying to our conditions, that is left hand side equal to right hand side, the loadings are also similar on both the sides, therefore it is a symmetric structure. Again let us consider this example. Is this a symmetric structure? No, this is not a symmetric structure, because the left hand side contains this one additional horizontal force which is not present on the right hand side. Therefore this is not a symmetric structure, or it is an asymmetric structure. Is this a symmetric structure? Yes, it is. So I hope you have got a fair idea about what is symmetric and asymmetric. But wait, is this a symmetric structure? No, this is not a symmetric structure, though it contains columns of equal heights, equal cross-sectional areas. Loading is also similar on both the sides, that is left hand side loading is equal to the right hand side loadings. But if you closely look at the supports, here it is a hinge support and here it is a fixed support. So with the geometry and the loading, the supports should also be equal on both the sides, or support should also be similar on both the sides. Then it will be categorized as a symmetric structure. For this particular case it is an asymmetric case. Now this is a beam, and let us draw a center line that is at the center of this beam. The left part of this section is exactly similar to the right part of the section, therefore it is a symmetric structure. In this case, is it a symmetric structure? No, the left part has a loading which is additional to the right part, therefore it is not a symmetric structure. Is this a symmetric structure? The left part contains the first segment having an additional cross-sectional area, and the right part does not. So it is not a symmetric structure, it is an asymmetric structure. So I hope you have got a fair idea about what is symmetric and asymmetric structures. Now let's start with our main topic, that is MDM in one step. Okay, so the first step in MDM is always finding fixed end moments. Here we need to find the fixed end moment only for the half of this beam, because it is symmetric, that is this half is exactly equal to the right side half. Therefore it is okay if you find the fixed end moments for only the left part of the beam, that is MFAB, MFBA and MFBC. So MFAB is minus 5 into 2 square into 3 by 5 square. This is for a point load, and the fixed end moment is given as WB square A by L square. And since it is having a anti-clockwise nature, therefore we give it a negative sign. So it is minus 2.4 kilonewton meter. MFB is 5 into 3 square into 2 by 5 square. Again the same formula here, that is W A square B by L square, and it is positive because it is a clockwise fixed end moment. MFBC is minus 10 into 4 square by 12, that is minus 40 by 3, and this is I hope you must be knowing this formula. It is WL square by 12, and again it is negative because it's a anti-clockwise fixed end moment. Step 2 is finding the distribution factors. Here comes the main concept of this whole section or this whole structure. First of all, you must have noticed that this is a symmetric structure, and MDM can, as I said, can be only applied to a symmetric structure. So we can draw this line that is at the center of the whole structure, and then you need to cut it at this particular point. Cut at this particular point and then separate it. Once the right side part is separated, we only require the left hand side part, because since both are similar or both are symmetric, so we have to work only with one side of the part, and this right side should be vanished. Now where the portion where we cut it, we have to give a fixed support there. Okay, the portion where my structure was being cut, I have to give a fixed support. So let's draw our distribution factor table, which has joint, member relative stiffness, total relative stiffness and distribution factor. So there is only one joint here, that is one intermediate joint, that is B, and the members connecting to B are BA and BC. BA, BC. The relative stiffness for BA is, if you see the member BA, then the far off end is hinged, and the relative stiffness for far off end hinged is 3 EI by L. So 3 EI by L is 5 meter length. And for BC, this is the most important part of this particular method of MDM. If you see the far off end for BC, it is fixed, and the relative stiffness for far off end fixed is 4 EI by L. But since we have reduced the BC to half of its length, okay, we have neglected the right side structure, right? So we have cut this BC into half, so we have to multiply this relative stiffness by half. Okay, so it is equal to 4, and here it is 2i, so it is 4 into 2 EI by 2. This 2 is from this half side, and L is 4 meters. L you have to consider the whole length. Okay, you cannot consider the half length, you have to consider the whole length. And if I simplify this, I get it as EI. So when I sum it up, I get the total relative stiffness, which is equal to 8 by 5 EI. And to find distribution factor, I have to divide 3 EI by 5 by 8 EI by 5. I get 3 by 8 as distribution factor for BA, and the distribution factor for BC is 5 by 8. So we got distribution factors, and now comes our final moment distribution step. So we have drawn here this beam. I have just flattened its columns, that is I have reduced the above structure to a simple beam type. Like this column, I have flattened it out. Okay, so this is A, B and C here. So now I have written here the fixed end moments that we got from the step 1, and MFAB was minus 2.4, MFBA was 3.6, and MFBC was minus 40 by 3. We only need half of the structure for our moment distribution, because we have considered only the left part of the structure, and these are the distribution factors. That is, for BA it was 3 by 8, and for BC it was 5 by 8. So now let's start with our moment distribution iterations. If you see, this is a hinge support, so we have to release this particular fixed end moment. So I give a external 2.4 kilonewton meter moment here, and which has to be carried here, and it gets half when it is carried on the other side. It gets half, so half of 2.4 is 1.2, and then we sum it off again. So we got 0 moment at our hinge, which is required because hinge cannot carry any moment, external moments. Therefore we got our result as 0, and this is what we wanted here. At this particular joint, 3.6 plus 1.2, we get 4.8, and here it is minus 40 by 3. So now we'll start our iterations. First step 1 is to balancing step. So we'll just sum it up and write the negative of that. So 4.8 minus 40 by 3, I get minus 8.533, and to resist that minus 8.533, we have to externally apply plus 8.5333. This is my balancing step. If you don't know how these steps are derived, that is balancing step and the next step, that is distribution step, you can check my moment distribution method video, which is quite popular on my channel, and it has gained the most number of views. So I'll just post the link here in the show notes here. You can check that video and you will be able to get the concept of moment distribution. So balancing is done, that is 8.5333, and now the step of distribution. In distribution, we have to multiply this balancing with the respective distribution factors. So 8.5333 into 3 by 8 is 16 by 5, and 8.5333 into 5 by 8 is 16 by 3. We just add them up now because there is nothing that we can do further to this. We cannot carry this here because it is a hinge. We don't carry it on the hinge. We cannot carry it here because the structure has been terminated abruptly at the half, so there is no support to carry this particular moment as well. Therefore we need to terminate our moment distribution iterations, and then we sum it up. We get here 0 plus 8 minus 8, and that's it. Your moment distribution in one step is done. So this is our final moments that we have written here. Under A, that is hinge, it is 0. Under B, it is BA, it is plus 8. BC, it is minus 8. CB, it is plus 8. CD, it is minus 8, and again 0. So whatever we got here in the left hand side, we just have to replicate them on the right hand side because the structure is symmetric. And this completes your final bending moment diagram for this particular frame. And this is how moment distribution in one step is done. I hope you understood this particular concept, and I hope this information was valuable to you. Please friends, like, share and subscribe this channel, and thank you so much. Hope to see you in the next video.